My name is Alexander Stumpf and I welcome you to my short presentation. How can we achieve fully autonomous leg locomotion? From a planning perspective, the goal is to achieve autonomous locomotion in unknown terrain, which includes finding suitable footholds in rough terrain. In the past, this was often done manually, which is a tedious and slow task as shown in the video. One of the first attempts for continuous walking in rough terrain was conducted by Fallon et al. But the question remained how such a sophisticated approach can be generalized so that it can be used by a wide range of different legged robots with respect to kinematics, control schemes, and APIs. Our new approach is to consider the entire sense plan act cycle in a single framework. In this work, we present a new holistic approach named Leg Locomotion Library, which includes important tools for generating suitable terrain models, blending feasible sequences of footsteps in challenging terrain, and finally bringing them into execution. Our main goal is to create a framework that can be used by many different legged robots. Our new modular terrain generator uses plugins that allow us to freely compose our world modeling processing chain and using different data sources and aggregation data structures. It provides an elevation map with optionally available color data and surface normals, which are used for our presented footstep planning approach. In our previous work, we showed how to traverse sloping terrain by snapping the center of the sole to the ground. However, this method is not suitable for highly irregular terrain. To cross highly challenging scenarios, such as the bottleneck test, we have to take advantage of a planar-shaped foot. Therefore, this work includes a new foothold estimation approach that allows our footstep planner to find feasible solutions in irregular terrain, where feasible foot support polygons using non-contiguous contexts must be found. Currently, footstep planning systems are usually tied to their target systems and are not interoperable. Our contribution consists of a novel generalized formulation for search-based footstep planning that makes no specific assumptions about the robot kinematics, such as the number of legs, or the used locomotion control schemes, and thus can be applied to a variety of different types of walking robots. Footholds and a single floating base are the basic elements of our new state action model representing the corresponding robot body parts. The floating base and each foothold that is in contact with the environment form the state. The step data structure includes all atomic actions, for example changes of the foot contacts, describing the transition between states. This new model is used to dynamically construct a graph from a predefined action set in which the best path is found using search-based algorithms such as A*. This new formulation also includes a generalized gate generation approach that allows us to use non-cyclic gates. An intelligent adaptive state expansion allows us to dynamically switch strategies during planning, for example by sparse sampling in obstacle-free regions. Continuous walking requires smooth synchronization of the motion execution and planning pipeline. The new L3 step controller provides crucial tools such as step plan stitching while providing a generic infrastructure to bridge both systems. Finally, we conclude our work by demonstrating continuous walking using our presented L3 framework. Here, our methods enables the animal robot to explore the terrain, continuously replan, and seamlessly extends the step queue until it successfully reaches the goal. The framework is available as open source in GitLab and fully integrated with ROS.